You can see the azimuths listed here, and then the horizontal distances that you see are those distances we measured in the field. So these first few lines showing the station and the line between each pair of stations, the corrected azimuth of each line, that is, the azimuth computed from adjusted interior angles, plus the horizontal distance, that is measured data. When we compute this data, we're going to come up with what we call latitudes and departures. And those latitudes and departures are simply the changes in northing and the changes in easting. Northing is what we call distance in the y direction, and easting is distance in the x direction. I have an example that shows how this whole process works. So let me switch screens here a little bit, and I want to show you a computational example along with a drawing of it. I have a spreadsheet that does the same thing as what you see on the page we were just viewing in your orange book. And this particular traverse has, I believe, 10 sides. This particular traverse, the sum of those sides is almost 12,500 feet. Here is a map view of our traverse, and in this traverse, it started on a known point. In fact, I can tell you that the coordinates of point 100, which is at this vertex, were known to be, actually assumed to be, a northing of 10,000 and an easting of 20,000. We started out with our instrument at, say, point 101, and we measured the distance from 101 to 100 at 1,251.44 feet. And here is an azimuth, a known azimuth, going from 100 to 101. And then we measured this interior angle, 171. So sitting at 101, backsighting 100, measured 171 to a foresight at 102. Then picked up the instrument, set it at 102, backsighted 101, reshot that distance, and turned this angle, 109.0916, and shot a distance of 2012.65 to 0.103. You know that every measurement contains error. So let's take a look and see what happens here at the beginning point. Our original point, 100, has a coordinate assigned to it of 10,000, 20,000. That's 10,000 in the northing, 20,000 in the easting. But our measurements are going to cause us to have a misclosure. When we've measured everything, and, this is very important, and after we have adjusted the errors in our interior angles and computed azimuths, then my calculated position of point 100 does not come up to the original location. Why? Well, there is still error contained in those angular computations. We said we don't know the size of the error or the location of the error, but we have applied a correction evenly to all the angles. Well, there's error in our error distribution, isn't there? So there's some inherent error still there, plus one of the error sources we haven't mentioned yet is in distance measurement. Naturally, there has to be some error in the distance measurement, and this error that you see here between the calculated point 100 and the original point 100 is really the sum of the two effects. Residual angular error after the correction of the angles, and uncompensated distance errors. In our case here, the change in northing between the 2 points is 29 hundredths of a foot. The difference in easting is 0.24 or 24 hundredths of a foot. And then the hypotenuse of a triangle formed by those two errors is 0.377. Now that's pretty remarkable considering this whole thing is over 2 miles long. Nonetheless, it is an error that we very often need to correct. Here's the moral of this story. Just as we correct bench circuits, our aim is to correct this traverse so this calculated point 100 will end up moved atop the original point 100. Well, if 0.100 shifts, then necessarily all the points between the beginning of the survey and the end are going to shift by an appropriate amount. In this spreadsheet, I have set this up so that I've got my computations happening automatically. For instance, the leg that goes from 0.100 to 101, it has an azimuth that we have plugged in here. It has a horizontal distance that we measured. The latitude that you compute is the change in northing, and the departure is the change in easting. Let me switch back to my drawing and illustrate that. In fact, I'll tell you what, I'm going to illustrate it here on point 101 to 102. Now, what's my distance? My change in northing from 101 to 102. I see that down here on the bottom of my screen it says 484.788. Well, let's see if that corresponds with our traverse. Indeed, from 101 to 102, the latitude, or that is the change in northing, is 484.788. And my change in easting should be 1312.213. Now let's check that. The change in easting is indeed 1312.213. And that agrees with my computations here. Everywhere around the traverse, computationally what I'm doing is breaking every vector down into its x and y components, or its northing and easting components. When you look carefully at this, you will see that without any kind of corrections for errors, if I start with a northing and easting for 0.100, and I don't correct for any errors, eventually I will get back to where I started from, but my computed position of 0.100 is not 10,000, 20,000. In fact, the numbers you see here agree with our drawing. You can see that we're off by the values you see here, 29 hundredths in the northing and 24 hundredths in the easting. How do we numerically correct? We use a thing we call the compass rule. The compass rule, simply put, takes the size of our error and distributes it based on the length of each polygon side. So how do we get that? If I sum my latitude column, that's my column G, and my column H, what I will find is the sum of all my latitudes, that is the sum of all the changes in northing, come out to be non-zero. In this case, 29 hundredths. A positive 29 hundredths. The sum of all my departures, that is my changes in easting, is a negative 24 hundredths. Well, just like you corrected a negative 3 hundredths closure error on a level circuit with a positive 3 hundredths total correction, our correction for our northings will be opposite in sign. At the top of each column is a simple little formula. The correction in the latitude is the horizontal distance for that leg divided by the total traverse length, L. As you can see up here in my formula bar, and L is the total traverse length. So the longer the traverse leg, the greater portion of the correction is applied to that leg. I'm going to take, in the northing, I'm going to take 29 hundredths of error, and I'm going to distribute that error proportionally across all the legs. Well, of that 29 hundredths, look, my longest leg appears to be about a little over 2,000 feet. Well, 0.049 of that 2900 shows up there. Whereas if I look at a short leg down here that's only 287 feet, only 0.007, less than 1/100th of that correction gets applied there. We do this for not only the change in northing, which we call latitude, but also for the change in easting. So we have a correction for the latitude and the correction for the departures. You can know that you're doing this correctly when the error in latitude is equal in magnitude but opposite in sign from the sum of the latitude corrections. Likewise, the sum of the departure corrections should be equal in size and opposite in sign to the total error in departures. These two numbers should match, and then these two numbers should match. Well, once create those corrections, you simply need to apply them. So, this balanced latitude becomes the original latitude plus the correction to get the balanced latitude. The balanced departure is simply the original departure plus the correction to get the balanced departure. I think you'll now understand that if I have applied these correctly, the sum of all these balanced latitudes and departures should become 0. Let's recap then. These two sums here were the errors in the latitude and departure. These two sums are the sums of the corrections. Once I apply the corrections to the erroneous latitudes and departures, then there should be no remaining error in those latitudes and departures. And I can prove that to myself by summing all of these latitudes and departures in these two columns. If they come to 0, then I know I have done that portion correctly. So then, how do I get northings and eastings out of this? Begin at my starting point, and then I simply apply 10,000 plus a negative 250.192, and it gives me 9749.81. And then I keep stair-stepping down. This, apply this, and I get that. This, I apply this, and I get that. I'm just stair-stepping down the spreadsheet here. And remember that each one of these changes in northing or changes in easting represents that x or y component of some vector that you measured on the ground. Then I know I've done it right when my ending point matches its original value. Let's talk about quality and how we define quality here. We said by looking at the drawing, we could see that the change in northing was 2900ths, the change in easting, or the error in the easting, was 2400ths, and my linear error is 0.377. That 0.377 is simply the hypotenuse of the triangle whose short sides are the easting error and the northing error. This shows up down here on my error in latitude and error in departure. The linear error can be readily calculated. That is, it is simply the hypotenuse of a right triangle whose two short sides are 2900ths and 2400ths. The relative error is simply a ratio of 1 over a number that comes from L divided by the linear error. You can see this summarized in your orange book. This is item 4C on page 38. We ask you to compute the relative error in the traverse and check it against the appropriate standard. So we divide L by the linear error, and we prefer to express the result as some fraction with a numerator of 1. And it's generally typical to round the denominator to the nearest 1,000. Now, this is an indication of positional error. You may recall that when we talked about taping, we're looking for an error standard of at least 1 in 5,000. That is 1 part error for every 5,000 parts measurement. Well, in our case here, this tells us, from a positional standpoint, we have 1 part error for every 33,100 parts of measurement. Simply put, at this level of quality, I can go a distance of over 33,000 feet before I accumulate 1 foot of error. That's pretty good. We can live with that. But is it good enough? This brings us to our discussion of accuracy standards. The American Congress on Surveying and Mapping is a member organization of the National Society of Professional Surveyors, and this is a standard that they have used for a long time to set standards for acceptable accuracy in land title surveys. And land title surveys are often used by commercial lending institutions who require a survey, a boundary survey, and perhaps a planimetric or topographic survey of the improvements on the site as evidence of the improvements and the legal status of the very things that they are financing. Now please understand, these particular standards were developed in the pre-total station days. So they make reference to methods we typically don't use anymore, but they are instructional in helping you understand what is acceptable accuracy. We typically don't measure to direct and to reverse, but we do pay very close attention to our angular closure. That is, if the number of stations in our traverse is 4 stations, then the acceptable angular closure error would be 10 seconds times the square root of the number of stations. In this case, if we have 4 stations, n equals 4, then the square root of 4 is 2. 2 times 10 is 20 seconds. That would mean that 20 seconds would be our allowable angular error for that particular survey. Here you can see a figure that very closely resembles what you saw in the subsequent pages here. And as they got to the end of this survey, they discovered that yes, our closure is 539, 59, 40. That gives us a 20-second error. And we have 5 sides, so the square root of 5 gives us 2.24, and 10 seconds times the square root of 5 gives us 22.4 seconds allowable error. Well, we have come in under that, so our angular error is okay. Well, what about that positional error? By the ALTA standards, they're looking for at least 1 in 15,000. And to be honest, in today's standards, 1 in 15,000 is fairly easy to hit. I've had good instrument operators routinely hit 1 in 50,000. On a really good day, we might squeeze out 1 in 100,000. We look at this as older standards, but they are instructive for helping us determine, I guess you could say, industry-accepted accuracy practices. So here in this case, we can see that our linear error shows up here as part of the traverse computations. We don't have a good way necessarily of knowing what this is until we have done the traverse computations. We can know what our angular closure is in the field. We can sum that up in the field before even tearing the instrument down from the last setup. But our relative error is something we determine in our computations. Generally, with today's technology, we can measure distances more accurately than angles. Therefore, the relative error is usually the easier of the two for us to hit.